Okay, so if the goal is to find what the original function is and we're given the derivative, we're given the derivative. What we want to do is we want to take the antiderivative of that derivative, because that helps us to take that step back to what the function is. So I apply my little integral symbol here to show that I'm taking the antiderivative. I apply that to 1 plus 1 over x squared. Right, 1 plus 1 over x squared is my derivative. Remember the dx, the differential is on there for notation's sake. It's part of taking the antiderivative here. So taking the antiderivative of 1 plus 1 over x squared. All right, before I get going on this, techniques we've used in the past when we take a derivative involve incorporating some negative exponents, right? We got 1 over x squared here. Makes more sense to write that as x to the negative second. Especially when we take an antiderivative and the only real rule we have has to do with powers. I need to see what that power is on that x. So taking the antiderivative of 1 plus x to the negative second, I start with that 1. That 1 is a constant. The rule in taking the antiderivative when you have a constant is you attach an x. So you have 1x. Again, if we want to make sense of that rule, take the derivative of x. What do you get? You get 1, right? That's how you check yourself. Okay, we're adding on. For the x to the negative second, the only real rule we have for antiderivatives dealing with power is add a 1 to the power. So if we add a 1 to the power, well, we get negative 1, right? And then if we continue with that rule, we're taking the reciprocal of that power, which is negative 1, and that's getting multiplied to the front. So negative 1 gets multiplied to the front here. That completes the antiderivative on each of these terms, meaning the only thing left to do is add on my constant.
With the reciprocal, like 1 would be negative 1. Wait, what did you say about the reciprocal?
All right, so what we found here is our original function, because we took the antiderivative of the derivative of that function. So f of x equals x. And since I got the negative 1 there, yeah, I'll say minus. In fact, since I have a negative 1 there as a power on the x, I'll say minus 1 over x. All of that plus c. Goal again is find the function. To find the function, we need to figure out what the constant value is. To figure out what the constant value is, we got to take some additional information that's given up here, like f of 1 equals 1. What that means is I take 1, I plug in for x, I get 1 back for the value of the function, right? So f of 1, plugging in 1 for x, that would equal 1 minus, well, 1 over 1, so just 1, plus c, right? And then f of 1 itself, that equals 1. So right now we've got this equation building where I've got 1 equals 1 minus 1 plus c. If you solve for c, obviously 1 minus 1 is 0, so c is just going to equal 1. So find what the original function is. We got the foundation for it right here. Got to figure out what c is, so I've got to insert in that value for c I've now found. I could say, therefore, f of x, my function, equals x minus 1 over x plus 1. So what we have here is a point on the original function. We basically got the formula makeup to find the slope of the tangent line. We got to find the original function and the value of that function when 2 is plugged in. So really, we got to find f of x. Right? Because if we know what f of x is, it'll be easy to find f of 2. And if you decipher the information that's given, knowing that this point lies on that function that we're trying to find, that means if I got a point of 1, 6, f of 1 must equal 6. Right? Take the x, plug in, get the y back. All right, other given information. I know the formula for finding the slope of the tangent line. What's that always connect to? That slope idea. What's that always connect to? Connects to the derivative, doesn't it? If I know the formula for finding the slope of a tangent line, doesn't that give me the derivative as well? So I could say that f prime of x equals 2x plus 1. And if I'm trying to find what the original function is, well, I can do what I just did on that last example, right? Take the antiderivative of 2x plus 1. Whatever that gives me the foundation for my function. So taking that antiderivative, this is x to the first, obviously. If you add 1 to that power, we're going to have x to the second. We take the reciprocal of that 2, which is 1/2. We multiply to the 2 that was originally in front, and we get 1 back. So x squared is the antiderivative of 2x. We add on, now taking the antiderivative of 1, that's just a constant. So attach an x to that 1. We've taken the antiderivative of both terms, add c for good measure, and like I said, the result we get here, that's our function. The thing is, we need to know the value of the constant. So to find the value of the constant, we go back to knowing that f of 1 equals 6. If I plug in 1 for all the x's, got f of 1 equals 1 squared plus 1 plus c. Of course, f of 1 is just 6, right? So there's an equation. 6 equals essentially 1 plus 1 plus c. Solve for c. C is going to equal 4, right? 6 equals 2 plus c. So c equals 4. Take that value of 4, plug back in up here for c. Our function f of x equals x squared plus x plus 4. If the question was find f of x, we'd be done, but the question is find f of 2, so take 2 and plug in. 2 squared plus 2 plus 4. We could say f of 2, or therefore f of 2 equals 10. So you got this root on the t, right? Okay. Got a couple things there. You've got the root on the t, so you know this is t to the 1/2. And then sure, we've been doing this a lot with taking derivatives. If you bump that up, we can create a negative exponent. So we can rewrite this problem as the integral applied, because we're still taking the antiderivative here, right? We're only simplifying the function at this point. That integral is applied to t to the negative 1/2, because we're bringing that up, times this quantity that I have on top, t cubed plus 2t squared. Yeah, integral notation stays here because we still haven't taken the antiderivative. So what this allows us to do, this allows us to take this t to the negative 1/2 and multiply it through. Right, as far as this quantity is concerned, the power on that quantity is just 1. So I can multiply through. I can distribute it. When I do that, well, multiplying like bases here, going to get that base of t. Got to add your exponents, so negative 1/2 plus 3. That's 5/2. Plus, take t to the negative 1/2 times 2t to the second. We've got 2. Keep your common base of t. Adding your powers, negative 1/2 and 2. Negative 1/2 and 2 added together to be 3/2. All that dt. We've had to do some simplifying, but if you look at what's left now, we've got 2 individual terms where we want to take the antiderivative, apply to each of those individual terms, it won't be too bad. If you've got t to the 5/2, add 1 to the 5/2. Well, adding 1 to the 5/2, I get 7/2. All right, so we're taking the reciprocal of 7/2, which is 2/7. We're multiplying that to what was originally in front, and originally in front we had a 1, so we just have 2/7 in front now. We are adding on, got this 2t to the 3/2, so add 1 to the power 3/2. If you add 1 to the power 3/2, you get 5/2. You take the reciprocal of 5/2, which is 2/5. You multiply that to the 2 that's originally in front. 2/5 times 2, 4/5. Taking the antiderivative as it applies to each term. Only thing left to do, add your constant. All right, so another example here where we got to simplify the function a little bit before we take the antiderivative. In simplifying the function here, it'd be pretty easy just to take this x to the second, bump it up, this x to the fourth, bump it up, and make those negative exponents. So integral symbol stays because we're still going to have to take the antiderivative. Bumping up those terms, we've got 3x to the negative second plus 5x to the negative fourth, all of that dx. We got some individual terms to work with here, where if we apply the antiderivative now and the rules that we know to each of those individual terms, all we got to do is add 1 to the power to get started. If you add 1 to this power, we get x to the negative first. We take that reciprocal, so reciprocal of -1 is -1. We multiply the value that's originally in front of the term. So that 3, we multiply by -1, we get -3. -3x to the negative first. We are adding on over here the 5x to the negative fourth, so add 1 to that power -4. If you add 1, you get -3. If you take the reciprocal of -3, you get -1/3. If you take -1/3, you multiply the 5 in front, you get -5/3. Apply the antiderivative to each of the individual terms. Add your constant. Don't have to simplify, so we're finished.